Okay, so let's begin. Well, some people think that the professors should be too serious to use the Facebook. Well, this is my Facebook account. This is a picture that just arrived today from another professor in the physics department. And well, I kind of like it. That's why I wanted to share it. This is the difference between information and knowledge. And unfortunately, our education system, including your education in this department, will be mainly based on information. So that is what we are doing in the lectures. In the lectures, we are trying to give you bits of information about this, about that, but we are not really stressing the connections between the information. You will be taking many courses in this department. Like now you are taking the mechanics course. Probably this is the general physics course, and probably this is the only course which covers a wide variety of subjects, so you can make various connections between these subjects. In most of the other courses, like next year you will be taking mathematical methods for physicists, where you will learn mathematical tricks to deal with the equations that we see. And in the following years, you will take classical mechanics, where you will have some other tools to deal with the problems of nature, electromagnetic theory. And we are teaching you those, we are giving you those information as if they are unrelated. And that is what most students keep thinking. They learn some tricks in the mathematical physics course, but they don't think how to apply it on the electromagnetic theory. But that is what is more important than the information. I mean, if you don't have these connections, if you cannot make these connections between the information, independent of how much information you have, you will not be able to make use of it. Less information, more connections between the information, you will be able to apply it to more different problems. This is, I think, this is something that you should keep in mind throughout your education career. So how are the things that you learn are related with each other? Now let's come to today's subject. Today, this week, well, today at least, we will be discussing fluids. Now, fluids are a difficult subject to study. If you think of what we have done until now, we started with the point particle, which was the easiest problem that we can deal with. We had the projectile motion, we had the force, we defined the work, the relation with the energy. And then in the last several weeks, we started dealing large objects, extended objects, but still rigid bodies. We started dealing with rotations. And you know more than I do how complicated the problem becomes when you take the rotations into account. But nevertheless, that was a rigid body. If you just count how many different ways a rigid body can move, okay, there's only 3 translational motions. It can move in the X, Y, or Z direction. Well, it can also rotate around 3 different axes. It can rotate around the X-axis, around the Y-axis, around the Z-axis. So a rigid body can do at most 6 different kinds of motion. 3 translation, 3 rotations. But when you think of a fluid, it is a mess. Well, it is a mess. It becomes mess. Now, when we talk about the fluids, we don't always mean the liquids. Now, the gas, in a sense, is also a fluid. Most solids, under certain conditions, they behave like a fluid. For example, plastic. Most of the plastic containers that you have, they are made using the fluid properties of the plastic. If you put it under extreme pressure, the plastic just starts to flow. And under those circumstances, the plastic is also a fluid. Now we will start with some properties. We will be dealing with the simplest case of a fluid. We will come to that, what the simplest case is. Now let's start with certain discussions. First, the pressure. Now, this is your friend's breakfast, so I need to give it back. There's liquid inside, and I'm sure it is most of you's experience that if you take this bottle and just press from the sides, the liquid just comes out. Okay, so that is some mass accelerating from inside and going outside. Now, if you think of how that works, let's go to a clean page. Okay, so we have this bottle, which is almost closed. So we have this pipe inside, inside there is the liquid. And when you apply some force from the sides, you squeeze it from the sides, the force. Well, there is also liquid inside. So it is filled with liquid up to this level. When you are squeezing it, you are applying a force here. Well, the force that you apply is at this point. But somehow, that force is transferred into liquid in this column, and that column of fluid just goes up and then out. Now, once it gets out, the remaining motion is more or less projectile motion. It just makes a projectile motion as a point mass, more or less. Now, a few things to note. By just holding it, I'm exerting some force, even some vertical force. There is some force exerted in this direction, but that is not enough. But as I'm exerting some force on this thing, the system is in equilibrium, there should be some force also that the liquid is exerting on me. So there's force being exerted in this direction. There's a balancing force that the liquid is exerting on the size of this, whatever this is. And so there's some force inside the liquid also. Well, let's try something else. Well, there's liquid inside. It's not falling down. So if it's not falling down, we know that there is the weight, at least. The weight of the fluid is trying to push it out of the bottle. But there should be some other force that is balancing it. So these are at least some of the things that we would like to discuss. Thank you. Now, one important property of liquids will be its density. Now, the way we define the density of a fluid is, well, the density, it is something that you are probably already familiar with. You just take some volume of a liquid, measure its mass. We know how to measure the mass already. So the mass per volume is what we define as the density. This concept is something that we will be using quite often when dealing with fluids. Now, when you are dealing with fluids, let's say one fluid is the sea, you have huge amounts of water, and when you are dealing with the oceans, you wouldn't like to deal with all of the ocean at the same time. You would rather deal with the local properties of the ocean, the properties that you can measure here, rather than just deal with everything. And density is like a local mass. If I just imagine a very small volume here, then there's a mass corresponding to that volume. Well, the mass increases with the volume. So the mass itself is not a property of the material itself only. The mass is a property of the material plus the volume of that material. Now, when we divide by the volume, what we get, the density is a property of the material itself. When you say that, when you are talking about water, let's say, we know what its density is. Under normal conditions, the density can also change from time to time. But when you are tell me that, okay, I have some water at this temperature, at this pressure, we know what the density is. You don't need to specify me the size of the water. Now, let's come to the forces that we have. Now, if you take some glass of water, we know that in the absence of the glass, the water will not take this shape. It will just splay out without the glass. So the glass is kind of exerting some force on the water so as to keep its shape. But if the glass is exerting force on the water, that means the water is also exerting a force on the glass. So if you just imagine, well, this is the top. So if you just imagine some area of glass, just imagine that it's very small, so that the force density on the surface doesn't change. So there will be a force exerted by the water, on the surface, well, one thing, it should be perpendicular to the surface if the water is at rest. Now we are dealing with water at rest. So the speed of the water, you just pick a small volume element in the water, the speed of that volume element is 0. So we are looking at water at rest. If water is at rest, then the force that the water exerts on the glass should be perpendicular to the surface. Well, why? Basically because if you just imagine this is the surface. So the water exerts a force on the glass, which is in this, well, let's just imagine an arbitrary direction. If water exerts a force on the glass in this direction, then the glass exerts some force on the liquid, and Newton's third law just tells us that it has to be in the opposite direction and the same magnitude. So if this is the force that the water molecule exerts, the water molecules here exert on the glass, then this should be the force that the glass exerts on the liquid. But such a force has a perpendicular component and also a horizontal component. But if you are exerting a force in this direction, well, this component is, well, it should be necessary to keep the water. We all know that it tends to flow. If there is no, if we drill a hole over here, the water will just move out of the hole. So this force is necessary to balance that. But there is also this force. Well, this force is pushing the water upwards. So the water will, if this is the direction of the force exerted on the glass by the water, then the glass exerts this force on the liquid. So the liquid, since it has a perpendicular component, the liquid will start flowing upwards. So if this is the case, the liquid will flow upwards, just like in that case when we squeeze it, the liquid flows upwards because there's an unbalanced force over there. But we are assuming here that the liquid is at rest. So that was our initial assumption. Here we are dealing with a glass of water that is at rest. So there's no motion left. When you are pouring the water for the first time, of course there's some motion in the liquid, in the fluid, but we are assuming that we have waited long enough so that the liquid is stable. So when the stability is reached, the liquid is no longer flowing, such a component cannot exist. So the force is always perpendicular to the surface. That is one thing. Now the second thing, how do we define the pressure? Well, if we have this force, the pressure is defined as the magnitude of the force divided by the area. This is how we define the pressure. So we know that if you have a very small hole in a bottle, let's say, it's quite easy to hold that hole. If you have a larger hole, you need to exert a larger force. Well, let's see the definition. The pressure is the length of a vector. Well, the length is a number, divided by the area, which is also a number. So the pressure is defined as the ratio of two numbers, so it is a number. It is not a vector, it is a scalar. Pressure itself doesn't have a direction. But pressure doesn't need to have a direction. Because when we want to calculate the force, we had already said that the force is always perpendicular to the area. So if you want to calculate the force exerted on the side of this glass, so you need to calculate the pressure at that point, and then calculate well, it doesn't make sense to talk about the force acting on a point. you should talk about the force acting on an area. Well, the area has a perpendicular direction. The direction of the force is that perpendicular direction. And if you know the pressure, you just multiply the pressure with that area and you find the magnitude. And the perpendicular to the area gives you the direction of the force. But then there is this question. Well, in this definition, by the way, we had defined the pressure only on the surface of the glass. It is a force between the fluid and the glass. But that is not necessary. Pressure exists everywhere. So if you just imagine a glass, let's say, filled with a liquid, and you can just imagine such a volume of liquid. We have some volume of liquid. It has a mass. And since the water is at rest, all parts of it is at rest, that column of water is also at rest. But that means the forces acting on that column of water should be zero. It is not accelerating. So that is what Newton's second law tells us. If there is a net force, it should be accelerating. If it is not accelerating, the net force should be zero. On one hand, we know that there is a force exerted by the glass on this column of water in this direction. So there should be a balancing force. And we had already said that the force due to the pressure is always perpendicular to the surface. So the only possibility is if there is a force from the other side, from the right opposite side, the pressure, there should be a force here whose magnitude is equal to this one. So the pressure here should also be equal to the pressure over there, so that this column of water should be at rest. So this kind of tells us that the pressure is not just on the surface, the pressure is everywhere in the liquid, because this column has to be at rest. The forces should balance. Any questions up to this point? Now, up to now, the only thing we have discussed is that there should be such a force per area, such a pressure everywhere. So there are two questions to answer. What is the magnitude of this pressure? What is pressure everywhere? How can we calculate it? We know that it exists, we can define it. And secondly, how do we know that it is independent of the direction of the area? So we said that the pressure is the, if you go to the definition, pressure is the force over area, but rather than taking such a glass, I could have taken a glass that has a weird shape. I could have imagined such a flask, cup. So in this case, I should have taken an area in this direction. This would be my area. If that is the area that we are claiming that there is a force in this direction, perpendicularly upwards, well, almost perpendicular to the area. This is the force. And we define a pressure also here as F over A. Or I can just imagine, well, these are real areas on the surface, but I can still imagine, just imagine an area like that. I just imagine it. Of course, this line of water is stable. It means there are forces on both sides. If there will be forces on both sides, and they will be balancing. Or let's do it like this. I have this area, I can consider this volume. Well, I know that this area over here, let's call it A1, and this area over here, A2, they are different areas. So we are claiming that, in this example, we already know that the pressure here, P1, and the pressure here, P2, they should be equal. From that previous example, we had imagined a rectangle. Since it was just a rectangle, and the force is always perpendicular to the sides, to this side and to that side. So the force on this side should be equal to the force on that side, but the areas are equal. If the areas are equal, the force per areas have to be also equal, the magnitude of the force per area. So that just tells me that the pressures on this side and on the other side, they have to be equal. But here we have a different example. Now we have some area over here. Let me just draw it a bit enlarged. So I have some area over here. I have another area on the other side. So here I have an area A2. Here I have an area A1. There's some pressure over here. I'm just assuming that this is still horizontal. We will see what happens when this thing is vertical. So there is a force acting here. Let's call it F1. And there is another force acting on A2. Well, its direction, it has to be perpendicular to the area. So it should have such a direction, F2. Of course, there will be other forces acting on my system. There will be a force acting on this area in the downward direction. And there will be another force acting on this area, which will be in the upward direction. But for the time being, let's just concentrate in the horizontal motion. And let us assume that this angle over here is theta. Now, what do we know? This volume of water, this is just the volume of water, the volume over here. This volume, I'm kind of enlarged it. Now, this volume of water is not accelerating because we assumed from the beginning that the water is at rest. Okay, so if it is not accelerating, it is not accelerating in the horizontal direction. If it is not accelerating in the horizontal direction, that means the net force acting on it on the horizontal direction is 0. Well, I have two forces that have a horizontal component. I have this F1 force. I just assume that this area is perpendicular, so that the F1 force is horizontal. And I also have this F2 force. F2 force is not horizontal, but it has a horizontal component. And if we want these two horizontal forces to cancel each other, I need to have F1 should be equal to F2 times cosine theta. Cosine or sine? Horizontal line. I'm looking at the forces in the horizontal direction. Okay. Yes. So it should be sine, no? Is it the sine theta or cosine theta? So is it the sine or the cosine? Okay, there is one answer. There was one answer who said it has to be the cosine. Now there is another answer who said it has to be sine. Come on, you have paper and pen in front of you. Yes. So is it the cosine theta or sine theta? Well, the first case was a cosine theta. Then we had this comment that it should be sine because the angle theta is small. If theta goes to 0, the horizontal component of F2 should go to 0. But the horizontal component of F2, if we say that it is the cosine, this doesn't go to 0 as theta goes to 0. It has to be sine. You see, this is my area. This is my area. This is F2. Here I have my A2 area. This angle here is theta. It should be sine. So this is my horizontal axis. Now this is perpendicular to the area. This angle here is also theta. If that is theta, that is 90 degrees, so this angle over here is pi over 2 minus theta. So the horizontal component, F1, should be equal to the horizontal component of F2, which is F2 times cosine pi over 2 minus theta. So this should be equal to F2 times sine theta. But if this is the case, this area here is A1, the force here is F1. Now the pressure 1, which is equal to F1 over A1, which is at the same time equal to F2 sine theta over A1, which I can write as F2 over A2, A2 times sine theta divided by A1. But this ratio is nothing but P2. So now the question is, what is this ratio? A2 times sine theta over A1. No, that is by, so this number over here, although it doesn't look like 1, it is F2. So that is F2 over A2. It should be P2. So P1, so what we have obtained is P1 is equal to P2 times A2 sine theta over A1. This is what we have obtained for the time being. Well, you probably already know that the pressure at this point and the pressure at that point, they should be equal. But what about this one? What should that be? Why is it 1? Well, A2 sine theta, it should be equal to A1, but why? Let's take this, let's just assume that this is our area A2. So how do you calculate this area? It is this length multiplied by this length. It's just a rectangle, so you just multiply the two sides of the rectangle and you get A2. It stays like this. Let's call this side the A side, the B side. A times B gives us A2. Now, this angle over here is what we call theta. Now, A side times the theta, sine theta, gives me this vertical side over here. So, this side multiplied with sine theta is nothing but this side. If you multiply with the horizontal side, okay, here is my hand. Let's just imagine that my hand is also a rectangle with the horizontal side equal to this side. Now this is A1 and this is A2. I just move them close to each other. Now the horizontal sides of both of these rectangles are equal. Well, I'm just taking a rectangular prism. This side multiplied with sine theta is the height of this A1 rectangle. So the height of this A1 rectangle times the width is nothing but the height of this rectangle times the width times sine theta. But that means the area of this one is equal to the area of this one times sine of theta. Let me draw it also here. So what I have is, this is my area. Okay? And this is my other area. I'm assuming that these two sides, I'm taking these two sides to be equal. So if this is B, this is also B. Now this side is A. Let me denote this side by A prime. And this angle over here is theta. This area over here is A1. This area over here is A2. A2 is nothing but AB. A1 is A prime B. This is how we define it. But A prime is nothing but A times sine theta. So it just tells me that A1 is equal to A prime B, which is equal to A sine theta times B. But this just tells me that this is equal to A2 times sine theta, or A2 sine theta divided by A1. This is equal to 1. Now, if you go to our previous derivation, we had shown that the pressure at this point and the pressure at this point, they are related by such a relation. And we have now shown that A1 sine theta, A2 sine theta divided by A1 is 1. So this ratio is always 1, whatever theta is. So this tells me that P1 and P2, they have to be equal. Well, this is nice because now we said that the pressure doesn't have any direction, but it is derived from some quantity which has a direction. Well, two quantities that have a direction. The area also can be imagined as having a direction. So we have to make sure that as this direction changes, pressure shouldn't change. Now here you can just imagine this area and this area, although in this case I have said that there is a finite length over here. This length can be 0. I never made use of this length. The only thing I made use of is that the horizontal component of this force and the horizontal component of this force, they have to be equal. And so if these two are, and also imagine that these areas are very small. I'm just exaggerating it. We are just looking at sub-millimeter squared areas. So they are just like a point. So if they are very close to each other, then we define the pressure. We can define the pressure at that point, whether by using this area or using this area. And we had just proven that whether we take this area or the other area, it doesn't change our result. So although we define the pressure from quantities that have direction, the direction of that quantity doesn't have any effect. So the long story short, to calculate the pressure, what you need to do is just imagine some area over there and just imagine that the area, calculate the force acting on that area, divide by the area, and then you will get the pressure. This is how you can measure pressure. So what should be the pressure? Well, again, Newton can help us on calculating the pressure in a liquid. Let's say we have a liquid filled with a glass filled with a liquid. Well, just do what we have done until now. Just imagine some liquid block. But this time it should be vertical. Now, in the previous cases, since we were considering only the horizontal forces, we didn't need to worry about the weight. But now we need to worry about the weight. Because we are looking for the vertical forces acting on my system now. Now let's say the bottom area is A. Let's just imagine the height is H. Now in the previous example, when we tipped the liquid it didn't flow out. It just tells us that there is also some force acting on it from outside, because we have a liquid block over there which is trying to go down out of the hole in the cup. There should be another force pushing it inside the cup so that it doesn't flow out. So let's just say that there is some force outside acting from the surface. Let's call it the pressure P0. Well, once we know the pressure P0, we can calculate the force by just multiplying it with the area. Now, this block of water is at rest. That is our starting assumption. Probably for some time we will just assume that liquid is always at rest. So whichever block we take, it is at rest, meaning that the net force acting on it is 0. So we have this block of water, liquid. Well, there is a downward force from P0, and we know that P0, that downward force has a magnitude P0 times A. Well, the other downward force acting on this block is its weight. Its weight is nothing but the mass density times the volume times G, the volume of this block. This should balance the upward force acting on it. Well, the upward force will be due to the pressure here. Here there will be another force due to the pressure in the bottom side. The upward force will have the strength, the pressure times the area. So this should be satisfied. Now the volume of this liquid is nothing but the area, the cross-sectional area, times the height. Now if you take the first equation and multiply it, divide it by the area, you will see that P0 plus rho times G times H is equal to the pressure. Well, this tells us two things, by the way, not just a single thing. It does allow us to calculate the pressure at a given depth in the liquid. Furthermore, it also tells us something else. So if I increase the pressure I exert on the top, that increase in the pressure is transferred throughout the liquid. So we know that the pressure at this depth is just the pressure at the top. So if I increase the pressure at the top, the pressure at this depth also increases immediately. So whatever pressure you exert from the outside, it will be distributed throughout the fluid. Well, that is in fact what causes the, well, if you imagine our first example, that is what causes this fluid block over here to flow out. So what we are doing here is by exerting some force over here, we are increasing the pressure. So you see, if the force that we apply is equal to the pressure, nothing will change. Since we are squeezing the block, it just means that we are causing the part of the cup at this side to accelerate. That means we are exerting a larger force. If we are exerting a larger force, that means the force at this point in the liquid should also be increasing to some extent. So that is, we are increasing the pressure. If we are increasing the pressure at a point by some external forces, that pressure increase has to be transferred. So we had just derived that the P is equal to P0 plus mgh. So that change in the pressure has to be transferred throughout the liquid. And it also increases the pressure here, pressure acting on this column, which pushes this column of the liquid up out of the straw. Now this has some nice applications which we will study next hour. So any questions up to now? Now up to now what we have shown is we define some quantity called the pressure, which is a number. It's not a vector. The pressure doesn't have a direction. It is just like the tension force we had. Remember, in the case of the string, we defined the tension on the string. It didn't have a direction. But when you cut the string into two, if you just imagine that you cut the string into two, the tension just gave us the direction of the force, the magnitude of the force, and the direction of the force was parallel to the surface, parallel to the string. This idea is identical. In this case, we don't have a one-dimensional string, but we have an area. So the force is always perpendicular to that area. Independent of the magnitude of the force is independent of the direction of the area. And that magnitude we define the pressure as the pressure. The direction is determined by the area. So in the case of the string, the direction of the tension force was tangential to the string. In this case, the direction of this pressure force is perpendicular to the area. Questions up to this point? Coffee time. Morning coffee.